So good morning, ladies and gentlemen. Now I'm going to talk about the paper that is written by the largest number of authors in this event. So first of all, let me introduce my co-authors here. They are Professor Aylan Cohen and Professor Sefi Noah. Let's give a warm welcome to all of them. This paper was independently worked by 3 different groups. For those of you who are interested in this paper, unfortunately, you cannot find the full version. But the good news is that you can find 3. All of those 3 papers are available on the archive. This paper deals with 2 problems. The first one is online covering problem. When you are traveling outside in the world, for example, to the European Union or to the UK, then you may want to try a kind of short-term SIM card, which is named pay-as-you-go. For pay-as-you-go SIM card, first you buy some packs, and after then, you can use it. For example, on day 1, if you want to give a Skype phone call to your family, and you need 500 megabytes of data, then you will need to buy either the second pack or the third pack. But the difficult thing is that you don't know your needs in the future. On the second day, maybe you need to give a telephone call. In that case, you may want to buy the second pack. Or on the other hand, maybe you want to download some movie to watch on the airplane. In that sense, the third pack will suit you better. But just make sure your cell phone is not Galaxy Note 7. Okay. We can write this program in a mathematical way. Here, the vector x means the number of each packs we want to buy. And A is the matrix for the constraint. It is satisfied that each entry of A is non-negative. But however, A doesn't come in advance. Instead, it comes row by row. And each row of 8 means a new constraint. When a new constraint comes, you need to increase some dimensions of X to satisfy it. And in addition, if you want to increase some dimensions of X, you cannot decrease any other dimensions. This is the definition of online covering problem. And in this paper, we concentrate only on the fractional solution. For online covering problem, previous results are either about linear functions or the maximum of a set of linear functions. Well, in this paper, we generalized the result a lot. Which are the set of functions that are monotone, differentiable, convex, and also its gradient is monotone. For this kind of functions, we get OP log D over P performance ratio. Here, P is the super of a function. Basically, P means if f is polynomial function that satisfying all the conditions above, then P is the highest degree. And D means the density of A, which is always smaller than or equal to the total number of variables. And previous results can also be applied to this paper. For the linear functions, we get the same ratio as before. And for the maximum of linear functions, because it is not differentiable, we cannot apply the result to this framework directly. But instead, we can use the P norm to estimate the infinity norm. And we get an even better result than before, which removes the dependency on coefficients. And also, many other applications can be transformed to this framework and then be solved by it. Using this way, for most problems, they suffer by at most a log factor. But also, we can solve many problems that cannot be solved before using this way. So these are about online covering problem. Next, we are going to talk about the online packing one. Suppose you are the manager of a factory. You have some resources and you want to earn money by producing some products. When the first product becomes available, you need to decide immediately how many of this product you want to produce. For example, when the first product comes, it requires 60 wood and you can earn $3. Then you need to produce some of them because the program may end immediately. But however, you don't know future products either. For example, in this case, if you save some resource for the future products, you may earn more money. Okay. So we can also write this program in a mathematical way. Here, yj means how much profit of product J we want to produce. And C means the resources we have. But sometimes we can also buy some extra resources with some cost. This is the problem definition of the online packing. Similar to the online covering, it is also guaranteed that the matrix A is non-negative for each entry. And in round K, a new column of AT comes together with a new variable YK. And you can only change YK to maximize our profit in this round. And also, it must be feasible all the time. For this problem, previous results are all about separable cost functions. And well, in this paper, we generalize it to non-separable cost, which is the set of function that is convex polynomial with non-negative coefficients. And if it's a degree Q polynomial, then we can get OQ approximation ratio, performance ratio. It has also some applications. For example, the social welfare maximization with production cost. We generalize this problem from separable function to non-separable functions. Well, in the previous setting, we also get the same result. Next, I'm going to talk about some basic technique used in this paper. Now we have both the covering problem and the packing problem. And some of you may have noticed something about it. Actually, they are primal and dual of each other if G is the conjugate of F. So the definition of convex conjugate is the super of xz minus fx. To give you some intuition of convex conjugate, if f is a lower semi-continuous and convex function, then the conjugate of the conjugate is f itself. And also, if f is x to the power of a, then f conjugate is a polynomial with a power of a over a minus 1. The technique we use in this paper is called primal dual approach. We use the algorithm that is covered by Allen et al. In 2003, which is the linear cost function for online cover. So In this problem, there's a new constraint comes in each round together with a new variable in the due. So in the first round, y1 comes. So we increase y1 together with the primal variables x until the primal becomes feasible. Okay, and in the second round, y2 comes, and if the new primal constraint is already feasible, then we do not need to do anything. And in the third round, if the primal is not feasible, then we still do the same thing as the first round. So that is the main idea for the primal dual approach. We can, for the primal dual approach, we can get F competitive ratio for both primal and dual problem if both primal and dual are feasible and primal is bounded by F times of dual. Okay. We can prove this by weak duality because the dual of any dual solution is smaller than or equal to the optimal primal solution. Then we can prove the primal is F competitive. And similarly, we can prove that dual is also F competitive. Next, we are going to illustrate how the primal dual algorithm will apply to the online packing problem. Okay, so we still want to do the similar things as before, as the algorithm found by Allen et al. So in round K, we also increase YK and increase X and Z according to some function of YK. Okay. For Z, we can always trivially set set Z to be equal to ATY. But for X, we want to do something to find how X increase. We know that in offline optimal solution that X is gradient of F conjugate Z. But however, in online solution, we never want to do that. Think of the case that there's just one product available. Then, in the offline optimal, you want to use up all your resources to produce this product, right? So, but in online case, you never want to do that because future products maybe require less resources but more beneficial. In that case, we want to save some resources for the future. So that's the main idea. So one way to achieve this is to increase X more sharply so that the primal may become feasible at an earlier stage. And one way to do that is to set X to be the gradients of F conjugate rho of Z, where rho is greater than 1. Then now we have we can denote the primal as a function of Z. Now if we want to bound the ratio, we can also bound the dual with a function of Z. We can differentiate the summation of Y. In round K, if we differentiate the summation of Y, the ratio is 1. Okay, then we can have the inequality because we only increase the primal variables when it is not feasible. So the inequality is true. And then we just write this summation form with as the vector product. So we have the third equality. Then we integrating both sides from the beginning to the end of the round K, then we have the following inequality. We can have a lower bound of the dual solution. Therefore, we can have another target, is to optimize rho such that this inequality is true. Then we can get an F competitive ratio. For example, if F conjugate Z is the square of the summation of Zi, then if we choose rho to be 2, then we can get an approximation ratio of 4. The previous things are about the packing solution. And also we can get something about the covering solution. We know that if we solve the covering and packing problem at the same time, we cannot, for the primal problem, we cannot beat the lower bound of the dual problem. For example, for the primal, for the online covering with linear objective function, the dual lower bound is O log rho d, where rho is the ratio of the coefficients. But the primal lower bound is only O log d. If we want to get some ratio better than the dual lower bound, we need to do some trick. So we have two tricks to get rid of the dual lower bound. One trick is to allow the previous dual variables to decrease, which can be seen in the work by Bookbinder et al. And another way is to transform the program to another objective function, which can be seen in the paper of Chen et al. Okay. So we get a brief summary of this paper. We generalize the online covering problem from the linear objective function to convex objective function, and also from separable to non-separable. And for the online packing problem, we generalize the cost function from separable to non-separable. And the technique we use in this paper is called primal dual approach, and we use ventral duality in this paper. And also we can get better covering solution, but in any way, the packing solution is not so competitive with the packing, with the covering one. Okay, so do you have any questions?